All right, there we are. So questions from the homework.
Can you do 12A?
12A, absolutely. Let me have a look at what 12A is. So 12A. Yeah, that's kind of a review problem. Let me share my screen and we'll talk about it. So yeah, I threw this in here basically so that, well, it's kind of a tough topic and I was hoping that you guys would just review it a little bit. So this problem here, number 12, we give you the derivative of some function g. So you might remember these problems from the previous unit. You know, we give you the graph of not the original function, but the derivative of some function. And then we ask you questions about it. Hey, so this is the graph of the derivative of g. So this is the graph of g prime. And part A asks you to identify the x-coordinates of all the relative minimums and maximums of the original function, g of x, which is not shown. So be sure to include boundary points. Yeah, we haven't talked too much about boundary points, so maybe I'll say something about that. But let's start by sort of reminding ourselves, where do minimums and maximums occur? Mins and maxes occur at critical points, right? And critical points are places where the derivative is 0 or undefined. This is a graph of the derivative, and I do not see any places where that thing is undefined, but I do see a couple of places where it's 0, right? The derivative is definitely 0 here. It's -2, so that's a critical point of the original function. And the derivative is also 0 here at 4, so that's another critical point of the original function. So what I would say is that those two critical points are potential mins or maxes, but are they actually mins or maxes? -2, I claim, is not. I think -2 is some kind of a plateau. The reason why is, if you think about it, before -2, in other words, to the left of -2, the derivative is positive, right? And after -2, to the right of it, the derivative is still positive, which means the original function, not shown, was increasing to the left of -2, and then it continued increasing after -2. That's neither a min nor a max. That's some kind of a plateau. On the other hand, number 4, or at x equals 4, I think that is some kind of local min or max. Let's see which one it is. Well, before 4, to the left of it, the derivative is positive, as you can see. The value of the derivative is positive. So that means to the left of 4, the original function was increasing. And then to the right of 4, the derivative is negative, which means the original function is decreasing. So the original function switches from increasing to decreasing at 4, and that's characteristic of a local maximum. Okay, so I think 4 is a local maximum. As far as the question about boundary points, it's okay if you didn't follow that. That's kind of a preview of some later material, but basically, local minimums and maximums can also occur at boundary points. And I'll just do one of them as an example. Have a look at -4. That's a boundary point for the function. That's kind of the beginning of where the function's graph starts. And you might notice that the derivative is positive at that point. Okay, so the graph of the original function, let's think about the graph of the original function, which is not shown. That graph begins at -4, and it begins with a positive derivative, right? The derivative is positive there. Let's just think about what that means. I'll switch to my document camera. If we think about what that means, you know, you've got at -4, that's where the function begins, right? The original function g, it begins at -4. That's like the boundary point of the original function. And it starts off with a positive derivative. So it starts off looking like that, positive derivative, and it begins at -4. That means that's got to be a local min. okay? I mean, it's the smallest guy in the neighborhood. Okay, we'll talk more about boundary points being local mins and maxes in a later unit. That's just kind of a preview. Other questions from the homework? Rex.
I had a question on 7A.
7A, sure. Do. Sure. Okay, so let me share my screen again. Do you want me to just talk about the entire 7A?
Yeah, that'd be great.
Cool. So let me share my screen. So here's number 7. It says, consider finding the area bound by this function right here and the x-axis. Do they give you a graph of this? No, they don't. So I think we'll graph it. You could graph it on your calculator. I think for convenience, I'm just going to graph it on Desmos. And it says, part A, why wouldn't integrating that function from 0 to 2 give you the right answer? Well, to answer that question, we really have to consult the graph. So just for convenience, I'll graph it in Desmos. So let's have a look at what that function actually looks like. It's not really that obvious because it's a cubic polynomial. So let's have a look. So it's the function 4x to the third minus 12x squared plus 8x. All right, so here it is. And the question was asking you about the area bound by this function and the x-axis. So I believe that what that's referring to is the area included in this region right here. You can see that's bound by the graph and the x-axis. And also this area right here, okay? So the question is asking, what is the area of this region and this region put together? Now, if you simply integrate, like if you compute the integral of this function from 0 to 2, remember that the integral gives you the signed area, right? It treats regions below the x-axis as being negative. In other words, if you just integrated this function from 0 to 2, what it would give you is this area right here, it would treat as positive, and then it would subtract this area right here. I don't know what it would give you, but that's not what we want. If someone asks you for the area bound by the function and some other curve, they mean the regular old-fashioned area, right? If someone says area, they mean regular old-fashioned area. They don't mean this weird signed area concept, okay? So, so does that make sense for why the integral wouldn't give you the right answer? So I guess, how would you get the right answer? Well, you would have to compute 2 separate integrals, right? You would integrate from 0 to 1, and that would give you this area right here. It would be a positive number because that region is above the x-axis. And then separately, you would integrate that function from 1 to 2, okay? And that would give you a negative number. You would simply make that number positive, like take its absolute value, and then put it together with the first region, and that would give it to you. Is that okay? Candace?
So then what's the wording for when they do want the signs? Like when they want you to include the signs in your answer?
Yeah, so the question is, what's the wording that they'll use if they do want you to include the signs? First of all, people generally don't ask for that. If they want the signed area, they would ask for the integral, right? They'd just say find the integral. But if someone really wanted to put it into words, they'd call it probably the signed area, like I do. Rest assured, people ask for area. People generally do not ask for signed area. If it says, if they want the signed area, they'll either say signed area, or they'll just ask you for the integral, right? Because the integral produces the signed area. Does that make sense? Okay. Can probably take more questions if people have them. Other questions in the homework? Sophie.
For the last problem, I know we already talked about it, but on the answer key it says that another min is 5.
Yeah, I think I said that I was only going to talk about one of the boundary points, but yeah, that other boundary point, the boundary point on the right, is probably also some kind of a min or a max. Do you want me to go through that really quickly, just to?
Yeah, if it's not too much trouble.
No, I think we've got time. So yeah, so just returning to that problem, the last one. As I said, like how boundary points play into finding mins and maxes is kind of something that we haven't talked much about yet, and we will in a later unit. But yeah, so believe it or not, this guy right here, you know, that's the right boundary point, right? The original function is only defined up to 5. And if you notice, the derivative is negative at 5. I hope you guys all see that, right? The derivative is negative at 5. So let's think about what the original function must look like. The original function ends at 5, and at that time, or at that point, its derivative is negative. If I switch to my document camera, I'll show you what I mean by that. That's not what I meant to do. Here we go. So way over here, at 5, that's where the function ends. And we just saw that the derivative of the function is negative at this point. That means that when it reaches this other endpoint, like when it reaches the right boundary point of its domain, the function's decreasing. So something like that. Do you see that that would imply that this is also a local minimum? Yeah. Yeah, so technically the story behind local mins and maxes is that local minimums and maximums occur at critical points, and they can also occur at boundary points if you have any. But we'll get into that a later time. Any final questions from the homework? No? Cool. Okay, well, let's do some new stuff. There's not a lot of new materials. Oh, before I forget. Yeah, so we're gonna have a quiz on Wednesday, okay? And it's just on the what we've done so far in Unit 6. So that's days 1 through 4. So that's obviously the Riemann integral stuff, right? Or the Riemann sum stuff, right? The mid left point, right end point, midpoint, all that stuff, trapezoids. That was day 1. Day 2 was interpreting integrals in context, right? Like understanding what an integral gives you, right? And sort of looking at the units of the integral, and that tells you a little bit about what the integral is computing. That was day 2. And then day 3, which was the previous lesson, was the fundamental theorem of calculus, which, you know, says that a definite integral can be computed just by finding the antiderivative, right? And like evaluating it at the endpoints. So those 3 days are what it's going to be on. It's not like a big assessment or anything. It's more just like, there's not a lot that we can do with Wednesdays, you know what I mean? So it just sort of makes sense to have an assessment, even though we're not even close to done with the unit. We just thought it made sense. Anyway, as a result of that, what quarter will it be on? Quarter 3, I think. I believe. I don't think we had that discussion, but seeing as it's technically in quarter 3, I believe it's quarter 3. Yeah, since we'll have that quiz on Wednesday, the assignment that I'm giving out today is not due Wednesday, it's due the class after that. Is that okay? Okay. Yeah, so make sure you review the first few days of Unit 6 for Wednesday. Okay. All right. So let's do some new stuff. I don't have a lot of new stuff for you today. I mean, obviously it's a short class, so I can't really introduce a whole lot, you know, in one class, but okay. Yeah, let's take some notes. Yeah, so the topic is average value. Average value. Okay. There's not a lot to it. Basically, I'm going to give you one definition, and it's nothing other than a formula, and that's kind of all there is to it. There's not a lot going on conceptually. So yeah, so I'll give you a definition. So definition, let f of x be a function. The average value of f over the interval a to b. So this is the thing that I'm defining. I'm defining the average value of f over the interval is given by, so here's the formula, average value of f over the interval AB is equal to, and here's the formula for that, the average value of f over the interval, 1 over b minus a times the integral from a to b f of x dx. Okay, that's the definition of the average value of the function. Well, I mean, so I'll just give you a moment to finish writing that down, and I'll say a few words about it. So like, you know, I mean, what does the average value mean conceptually? I mean, I've given you a definition from this formula. In a certain sense, that's all you need to know. If you got a formula, then you can compute it. But what does it mean conceptually? Well, roughly speaking, the average value of a function f on an interval from a to b is kind of just like the typical value of the function during that time. You can kind of ask like, what's the typical value of the function during that time? And that's what this thing computes. It's a little tricky because if you think about averages, you obviously know how to compute an average, right? You add together the numbers in the data set and then you divide by the number of elements. That's the average. The weird thing about this concept here is that typically a function will take on an infinite number of different values over an interval. Are you with me? Like, if the graph of the function looks like this, then as you can see, like the function takes on technically an infinite number of different values, all these guys right here during that time. And so the usual process is sort of like adding together all the things and dividing by the number of things doesn't really make sense and doesn't really work. And that's why this integral appears here. Explaining exactly why this formula computes some kind of average value is kind of a long story. It's a little bit complicated, and I just won't get into it. I'll just ask you to have a little bit of faith that this thing actually does give you, in some sense, the typical value of the function during this time. I mean, if you computed the average value for this function over this interval, it would presumably give you something like, I don't know, around here, right? Maybe that seems like a typical value, sort of in the middle. But it's kind of, you know, it's kind of a weighted average. Like, if you computed it like this, like let's say your function looked like this, maybe it's like pretty flat, but then there's like a big spike, but it only happens for like a brief second, and then it goes back. The average value in this case would be not right in the middle, but rather more like right here. Basically, because most of the time, the function is this value right here. But then for a brief moment, it goes really high, and that kind of drags the average value up a little bit. Does that make sense? That's all that it is. Okay, so questions so far. Okay. All right, well, let's just do one example, and that's pretty much it. Okay. Find the average value of the function f of x equals 9 minus x squared over the interval -3 to 3. Okay. So let's just compute the average value. And then after I'm done computing it, we'll take a look at the graph and just kind of convince ourselves that that makes sense as an average value. Okay, so the average value of f over the interval from -3 to 3 is going to be what? Let's recall the formula. You start with 1 over b minus a. A and B, of course, are the left and right endpoints of the interval over which you're computing the average value. It's essentially just the width of the interval. Do you guys see that? Like if you're going from A to B, then B minus A is just the length of the interval. So yeah, in this case, that's going to be 1 over 3 minus -3, which of course is going to be 6. Times the integral from -3 to +3 of the function. So that's 9 minus x squared df. So I'm just directly applying the formula there. Okay, so now, you know, this is the problem that could have been on yesterday's worksheet. We're just trying to compute an integral. You know, we can use the fundamental theorem of calculus to evaluate this integral. We just have to find an antiderivative for the function, right? So let's compute. So 1 over 3 minus -3 is, of course, just 1 over 6. And then let's think about an antiderivative for this guy. I think that would be 9x minus 1/3 x to the third. Do you guys agree that if you take the derivative of this, you get this? Okay. And what do you need to do with that antiderivative? The fundamental theorem says you have to evaluate it from -3 to 3. Is that okay so far, guys? Okay. Alex, is that a question? Or no? Okay. All right. So that is 1/6. So I need to evaluate this whole thing at +3. I'm going to put some brackets here, basically, because this 1/6, you know, when I do the evaluation of this function, it's going to be this whole function evaluated at 3 minus the whole function evaluated at -3. And because of that, I'm going to have like 2 terms, and the 1/6 needs to hit both of them. So I'm going to put them in brackets to make sure the 1/6 hits everything. So evaluate this whole guy at 3. That's 9 times 3 minus 1/3 times 3 to the third. That's the expression evaluated here, minus this whole expression evaluated at -3. That's 9 times -3 minus 1/3 times -3 to the third parenthesis bracket. There's a lot of parentheses happening here. It's getting a little bit out of control. You need to be really careful with this stuff, right? There's a lot of minus signs, and be very careful when you're writing these things down. It's easy to make a sign error. Okay, so let's simplify. 1/6, that's 27. 3 to the third divided by 3 is essentially 3 squared. So that's just 9. Minus, okay, let's take a look at this guy. 9 times -3 is -27. Let's be very careful with the signs here. It's -3 to the third. That's an odd power, so it's going to be -27, right? Odd exponent. So this guy here, the -3 to the third, that's -27. But then it's being multiplied by -1/3. So it's actually a +9. Is that okay? The final term is positive. Okay, so 1/6. Let's see, what is this? That, of course, is 18. 27 minus 9. And then minus this is -18. So it's 18 minus -18, which is 1/6 times 36, which is 6. Hardest part about that problem was not the calculus. I think you'll agree, right? Hardest part about that problem was like the 20,000 parentheses and negative sign. Yeah, so that's the average value. Now, like, does that make sense? I mean, if you look at the graph, yeah, it kind of makes sense. Like, the maximum value of the function on that interval is 9. The function pretty much looks like this. And 6 is like here. So, does that make sense? I mean, more or less, it's reasonable. Okay. Questions on that? Okay. Good. All right. Well, yeah, so the worksheet is on Canvas. And as I said, it's, not due Thursday. Or it's not due Wednesday, it's due on Thursday. So make sure you prepare for the quiz.